Hello students, this is a video on the topic tests that we have on the Bodhee Prep Android app. So these tests are designed to help you understand whether you have generally prepared a topic or not, as in is the topic ready for the exam. Now, when should you be taking these tests? Whenever you complete a basic concept, have made some practice on that concept, it is advised that you go through these tests, take them in a timed manner, and once you've taken the test, then you go through the related video. And the video will give you a perspective of what could have been a good attempt, the kind of questions that you should be looking at, the solutions to those questions. And if you do like the test, there are more than 200 topic tests available on the Bodhee Prep app. The link for the app is in the description below. So please download the app and try to make the most of these tests. This video is about the test on divisibility rules, test number 5 on this topic. Overall, the test was, I think, moderate level of difficulty, and an attempt of net 6 correct questions would get you a 95 percentile plus in this test. In terms of time, I think the most of the questions were doable in reasonable amount of time. Some questions might have a spillover, but even considering that also, I think 20 to 23 minutes will be good enough to go through all the questions and get your net 6 questions correct. Looking at the questions, the first question says, how many 3-digit positive integers leave a remainder of 3 when divided by 5 and a remainder of 3 when divided by 7? So when we divide the number by 7, the remainder is 3. When we divide the number by 5, the remainder is 3. So we can say that when we divide the number, or the number will be the LCM of the divisor 7 and 5 plus the remainder that we are getting. So the smallest possible value of this number will be 38. LCM of 7 and 5 is 35 plus 3. To get further numbers, we will keep adding the LCM to this number. So the second number will be 38 plus 35, which is 73. The next number will be 73 plus 35, which will be 108, and so on. We are looking at 3-digit positive numbers. So the first number that we get is 38 plus 35 into 2. This is a 3-digit number, 108. If we keep doing this, 35 into 20 will be 700, 700, 140, 70, 910. 910 is a multiple of 35, 22, 24, 2, plus 70, 980, minus 1, plus 35, 945. So 24, 26, 27. 35 into 27, if we look at, 35 into 27 will be 27 into 7, 9, 4, 10 to the 14, 4, 18 into 5, 945. So 35 into 7 is 945. If we add 38 to that, we'll get 3, 1, 4, 6, 7, 8, 983. And therefore, our list of numbers starts from 108, goes on till 983. Multiples of 35 that are being used are from 2 to 27. The total number of numbers will be 27 minus 2 plus 1, which will be 26 in total, and that becomes the answer. In terms of level of difficulty, I think easy question, because the numbers are not very difficult. I think 1.5 minutes should be good enough to attempt this question. Let M be the number of 4-digit palindromes. Palindromes are the numbers which read the same from left and right side. So M is the 4-digit palindromes multiples of 9. N is the number of 4-digit palindromes multiples of 7. What is M plus N? Okay, so if we look at M, there are 4 digits. We are looking at multiples of 9. These 2 digits will be same. These 2 digits will be same. So the number has to be of the form, say, A, B, B, A. This is the palindrome. The sum of digits has to be 9. Clearly, 9 or a multiple of 9. Now, A plus B cannot add up to 4.5. And therefore, the sum will not be 9. The sum will be 18 for this entire thing. And therefore, we are looking at cases where A and B are 9. So this can happen when 1, 8 is there. So followed by 8, 1 will be a palindrome. Similarly, 2, 7, 3, 6, 4, 5, 5, 4, 6, 3, 7, 2, 8, 1, 9, 0. And then there will be one case where we have a number called 9999. This becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the palindromes that we have, which would be multiples of 9. So m becomes 10. What about n now? Now if I look at A, B, B, A, this can be written as 1001 into A plus B into 110. So this will give me A00A. This will give me BB0, which will add to get, which will add to give me ABBA. Now, if we have to divide this by 7, 1001 is 91 into 11, which is nothing but 13 into 7 into 11. So this part is already a multiple of 11. No matter what value we put for A, this will be a multiple of 7. We are to make sure that the number is divisible by 7, this thing should be divisible by 7. 110 is not divisible by 7, so that there are two possibilities. Either we put B as 0 or B as 7. So this part will become divisible by 7. And for each case, A could take any value from 1 to 9. For example, 1001, 1771, 2002, 2772, and so on. So B could be either 1 or 7. The middle number should be 00 or 77. And A could be any number from 1 to 9. So 9 options here and 2 options here. The value of n is 18. What is the value of m plus n? 10 plus 18, 28 becomes the answer. I think moderate level of difficulty question, 2.5 minutes should be good enough to answer this question. The only problem could be how do we check for multiples of 7, which is something that you'll have to figure out during the question. Otherwise, not a very difficult question to solve. How many positive integers D are there such that the remainder equals 8 when number 2018 divided by D gives us a remainder equal to 8. Therefore, we can say that 2018 minus 8 should be divisible by D, which means 2010 should be divisible by D. Also, since the remainder is 8, D has to be a value which is greater than 8. Because if I divide the number by 5, I cannot get a remainder that is 5 or more than 5. So we look at the factors of 2010, the numbers that will divide 2010. 2010 is 201 into 10. 201 will be 3 into 67. 1 into 10 into 2 into 5. So basically 2010 will be 2 into 3 into 5 into 67. Out of these, so if you look at the number of factors of 2010, that will be, there are 4 prime numbers with the power of 1. So 1 plus 1, 2 into 1 plus 1, 2 into 1 plus 1, 2 into 1 plus 1, 2, 16 factors will be there. So D can take 16 values, or number that can divide 2010 can take 16 values. But again, D has to be a number which is greater than 8 for sure. Only then will a remainder of 8 be there. If you look at the factors 1, 2, 3, 5, 6. 1, 2, 3, 5, 6. These factors that we can form from here, if you're looking at the 16 factors, the factors would be something like 1, 2, 3, 5, 6, 10, 1, 2, 3, 4, 5, 6, 10, 15, 30, and then correspondingly 67, 67 into 2, 5 into 67 into 3, 67 into 5, and so on. Till the last number will be the number n itself. So here we can see that these factors 1, 2, 3, 4, 5 and 6, which is 1, 2, 3, 4, 5. There are 5 factors which are not greater than 8. So the values that D can take are total 6 factors, out of which 5 factors are not greater than 8. So D can take any of the remaining 11 values, 10, 15, 30, 67, and so on. And whenever we divide 2018 by those numbers, these 11 numbers, we'll get a remainder of 8. So 11 becomes the answer. Again, I think an easy question. The only thing here is ability to count the number of factors and understand the fact that the divisor has to be greater than the remainder. 1.5 odd minutes should be good enough to answer this question. How many positive integers n are there such that n cube plus 100 is divisible by n plus 4? If we divide n cube plus 100 by n plus 4, we will get a quotient and a remainder in terms of n, or a constant remainder. To find this remainder, we can use the remainder theorem. We put n plus 4 is equal to 0, n is equal to minus 4, substitute that value in the dividend. So the remainder will be minus 4 cubed plus 100, which will be 36. Now, if I look at the expression n cube plus 100, this can be written as divisor, there will be some quotient into divisor plus the remainder, which is 36. We want to divide n cube plus 100 by n plus 4. So we divide this by n plus 4. Clearly, the first part is divisible, only this part is not. As long as 36 is divisible by n plus 4, the entire n cube plus 100 will be divisible by n plus 4. So n plus 4 has to be a factor of 36. If we look at 36, 36 is 2 square into 3 square, 4 into 9. So the factors are 1, 2, 3, 4, 6, 9, 12, 18, and 36. These are the factors of 36. So we start putting the value of n plus 4 as 1, 2, and so on. But what is also given is positive integer n. Since n plus 4 is positive, the value of n plus 4 has to be greater than 4. Because if n is positive, it has to be at least 1. From here, we'll get n is minus 3. So these factors are not used. We will use a value which is at least 5. So we get 1, 2, 3, 4, 5 cases where n plus 4 is 6, n plus 4 is 9, n plus 4 is 12. No need to write all of these cases. The answer is 5. But just to see what n plus 4 is 36. 6, 9, 12, 18, and 36 are the factors that we'll use. So n could be 2, n could be 5, n could be 8, n could be 14, n could be 32. How many positive integers? 5 positive integers are possible. I'd say a medium level of difficulty question. The only thing is factor theorem is used, and from there, working with 36 is not very difficult. The positive integer part had to be remembered. 2.5 minutes should be good enough to answer this question. If a 6-digit integer 123 AB is divisible by 99, divisibility by 99 means divisible by 9 and 11. For divisibility by 9, 1 plus 2 plus 3 plus 4 plus a plus b should be a multiple of 9. 4 plus 3, 7 plus 2, 9. This is the sum here is 9. So a plus b plus 1 should be 9, or a plus b plus 1 should be 18. Which means from here a plus b should be 8, or a plus b could be 17. Only one case is possible for this one, it is 9 and 8. But divisibility by 11 means b plus 4 plus 2, b plus 6 minus a plus 3 plus 1, a plus 3 plus 1, a plus 4. So b plus 6 minus a minus 4, which is b minus a plus 2. This should either be 0 or this should be 11. Can this be 11? Yes, when a is 0. This means b minus a will be, if b minus a plus 2 is equal to 0, this means a minus b will be equal to 2. B minus a is equal to minus 2. Multiplying by minus 1, a minus b is 2, or b minus a plus 2 is equal to 11, which means b minus a is equal to 9. We get two sets of equations. From the first one, a plus b is 8. From the second one, a minus b is 2. A plus b is 8. B minus a is 9. So I'm taking one equation from here, one equation from and combining. A plus b is 17. A minus b is 2. A plus b is 17. B minus a is 9. Now for the sum to be 17, the two numbers have to be 9 and 8, in which case the difference will be 1. So this case is obviously not happening. Coming here, if we add these two, 2a is equal to 10, a is equal to 5. If a is 5, b will be 3. Here, if we add 2b is equal to 17, b is equal to 8.5, cannot happen. So this is the only case that is possible. B will be 5, a will be 3, and therefore a square plus b square will be 3 square plus 5 square, which is 9 plus 25 is equal to 34 becomes the answer. Again, basic divisibility check, I'd say, and probably an easy question. should be able to do this in about 2 minutes just because there were a couple of basic cases that were formed. I have written the values reverse. This is 5, this is 3. This is 5, this is 3, but anyway, the answer will be 34. So yeah, I stick to what I said, moderate level of difficulty. For easy question, solving time may go up to about 2 minutes. Find the greatest integer n such that 2 raised to 9 divides 62018 minus 41009. We would somehow want to make base same or similar or power similar. We can see 2018, here it is 1009. 2018 is double of 1009. So what I'm doing it, I'm splitting 6 and writing 6 as 3 raised to power 2018 into 2 raised to power 2018 minus 4 can be written as 2 square raised to power 1009. This becomes 3 raised to power 2018 into 2 raised to power 2018 minus 2 raised to power 2018. Taking 2 raised to power 2018 common, we get 3 raised to power 2018 minus 1. Clearly, this entire part is divisible by 2 raised to power n. Let us see what is the highest power of 2 that we get from the second bracket. 3 raised to power 2018 minus 1 divided by 2 will give us a remainder of 3 becomes 2 plus 1. 2018 minus 1. So from here we'll get a remainder of 1 and minus 1. So this will be 0. So this is also divisible by 2 individually. If we check by 4, this becomes 4 minus 1 raised to power 2018 minus 1 divided by 4. From here we'll get minus 1 raised to power 2018, remainder of 1. From here minus 1, so overall remainder is again 0. So divisible by 4, another 2. If we check with 8, we'll get this becomes 9 raised to power 1009. Squaring 3, so 1009 is left. This is nothing but 8 plus 1 raised to power 1009 minus 1. From here we get a remainder of plus 1, from here minus 1. So overall remainder is 0. This is also divisible by 8. Checking for 16 then. This becomes the power of 3 close to 16 is 81. 3, 9, 27, 81. So we want to take the power of 3 as 4. 2018 is not divisible by 4, so we write it as 3 square into 3 raised to power 2016 minus 1 divided by 16. So this becomes 3 square 9 into, from here we can take out the 4, so 81, 3 raised to power 4, raised to power, here we'll have 504 remaining. Now 81 is 80 plus 1, so when we divide 9 into 80 plus 1 raised to power 504 by 16, we'll get a remainder of 1 from here multiplied by 9 and minus 1. So the remainder that we'll get is 8 overall, which means this term is not divisible by 16. Hence, we can write this term as 8 into something which is not a power of 2 anymore. So 8 into odd number b. This becomes 2 raised to power 2018 into 2 cube into b, which can be written as 2 raised to power 2021 into b. What is the highest power or what greatest integer n such that 2n divides this? The value of n can go up to 2021 and that becomes the answer. 2021 becomes the answer. Again, I'll say moderate level of difficulty question. The first step is easy. Then we just have to check that in the remaining term, what is the power of 2 that is left. 2.5 minutes should be good enough to answer the question. What is the largest prime p such that p square divides 28 factorial plus 29 factorial plus 30 factorial. N factorial is the product of all numbers, natural numbers from 1 to n. So we can write 29 factorial is nothing but 29 into 28 factorial. And 30 factorial is 30 into 29 into 28 factorial. Taking 28 factorial common, we get 1 plus 29 plus 30 into 29. This becomes 28 factorial into 30 plus 30 into 29, which further becomes 28 factorial. Taking 30 common, 29 plus 1, which is again 30. If we take 30 common from here, we'll be left with 1 plus 29, which becomes 30. So the value that we now have is 28 factorial into 30 into 30. We're looking at the largest prime so that p square divides the number. So if we look at 2, 3, 5, 7, 13, 11 first, 13, 17, and so on, which prime number has at least two multiples in this product? Clearly, 2 has many multiples, so power of 2 can be higher. 3 also has many multiples. 5 has 5, 10, 15, 20, and so on. 11 has 11, 22. The power of 11 that will divide this will be squared. Because in this entire thing, the multiples of 11 are only 11, 22. If we look at 13, again, the highest power that will divide this for 13 will be squared. Because multiple of 13 in this entire product is 13 and 26. There is no other multiple. For 17, we have 17 and 34. That is not possible. So 17 square will not divide this. Because if I write 28 factorial, which has 17 only once, multiplied by 30 and 30, this will be divisible by 17 only once. There will be no other part that will divide 17. Hence, the highest or the largest prime number p, such that p square divides this, will be 13. And that becomes my answer. That's not a very difficult question. Sorry. But not a very difficult question. It might take some time to figure out the how we are going to rationalize the overall expression. But even then, it is pretty obvious that 13 is the only number which is repeating twice in each of the terms. And so it will divide each of the terms. 2.5 minutes should be good enough to answer the question. It is known that 3x plus 5y is divisible by 37. Based on this, it can be concluded that ax plus 7y is also divisible by 37. The smallest possible value of a. Since the coefficient of y is given in both cases, I am saying I'll try to make them same first. Since 3x plus 5y is divisible by 37, LCM of 5 and 7 is 35. So I multiplied this by 7. 21x plus 35y will also be divisible by 37. Multiplying this by 7 will not change the divisibility. Also, we know that ax plus 7y is divisible by 37. Multiplying this by 5, 5ax plus 35y will also be divisible by 37. Now, if we compare these two, 35y is as it is. So this part is same. And therefore, from 21x, we should be able to reach a term 5a, which remains divisible by 37. Clearly, 21 is not divisible by 5a. So 5a cannot be 21. But what I can do is, I can add 37x here. If I add 37x here, divisibility by 37 will not be affected because this is divisible by 37, this is divisible by 37. And therefore, 21 plus 37, which is 58x plus 35y will be divisible by 37. Again, adding 37x will not change the divisibility. So 95x plus 35y will still be divisible by 37. As we can see, this is now multiple of 5. Since this is multiple of 5, we can say 5a could be equal to 95. And this is the first time this will happen because it's the first multiple of 5 that we get. So the smallest value. And therefore, a has to be 90. That becomes my answer. The other way of attempting this question would be putting values. So we put a set of values for x and y to get 37. Top of the mind, 5 into 5, 25. 3 into 4, 12 is 37. So if we put the values here, x is 4, y is 5. 4a plus 35 this should be divisible by 37. Now start putting the value of a, and whatever value of a we get, this becomes divisible by 37. That is the answer. I think this is a good question in terms of level of, or in terms of concept, it's a good question. So I'd call it a difficult question. 2.5, 3 minutes easily to solve the question. Find the number of positive integers less than or equal to 2016 that are divisible by 2 or 3 but are not 5. So when we check for 2, the first number divisible by 2 will be 2 into 1, which is 2. The last number divisible by 2 will be 2 into 1008, which is 2016. Now from here we'll take out multiples of 5. So first number will be 2 into 5, then 2 into 10 and so on. The last multiple of 5 before this is 2 into 1005. So what I'm saying is total numbers were 1008, and from these multiples of 5 are 1005 by 5, which is 201. So 807 multiples of 2, which do not include 5. If we look at 3, 3 into 1, 3, 3 into 2 and so on, there will be 3 into 5, 3 into 10 and so on going on. The last number will be 2016 by 3, which will be 3 into 6 3s are 18, 672. The multiple of 5 before 672 is 670. 670 by 5 is 134. 656 again. So total 672 numbers from 1 to 672. From that we subtract 670 by 5, which is 134. So we are left with 8, 12, 1, 3, 4, 3, 5. 538 multiples of 3, which does not include 5. Now we combine 2 and 3. The first multiple of 6 will be 6, then 12 and so on. There will be 6 into 5 as well somewhere. There will be 6 into 10 as well somewhere. The last number divisible by 6 will be 6 into 6 3s are 18. 2 1, 6 3s are 18. 336. Half of 672. This is 2016. The multiple of 5 before this is 335. 335 by 5 will be 67. So total 336 numbers. From that, 67 multiples of 5 are being removed. So this will give us 9167 62 320 336, and therefore multiples of 2 excluding 5 807, multiples of 3 excluding 5 538 added, minus the common multiples of 2 and 3 which are counted both in both places, so minus 269. This becomes 807. 538 minus 269 is 269. 807 plus 269 becomes 74. 1074 becomes the answer. Again, I'd say in easy question in concept, calculation might take a bit of time. 2.5 minutes, good enough to solve the question. The product of any two elements in the set 30, 54, n is divisible by the third. Then find the number of possible values of n. So 30 into 54 is divisible by n. 30 into n is divisible by 54. And 54 into n is divisible by 30. Now 30 is nothing but 6 into 5. 2 into 3 into 5. 54 is 27 into 2, so 3 cube into 2. This has to be divisible by n. So we get 2 square into 3 raised to power 4 into 5. Clearly the powers of 2, 3, 5 in n should be less than equal to 2, less than equal to 4, less than equal to 1 respectively. And there should be no other prime number in n. Only then will this division happen. Here, so from this I can say n could have powers of 2 as 0, 1 or 2, powers of 3 as 0, 1, 2, 3 or 4, and power of 5 as 0 or 1. 30, 54, 2, 3, 9, 27, 24. 1, 2, 3, 4. Now here 30 becomes 2 into 3 into 5. N is n. N is n. 54 is 3 cube into 2. 2 and 2 cancel, 3 cancel. So we left with 5 into n upon 3 square. Which means n has to have the power of 3 and at least 2. So these two cases go away. n has to have a power of 3, which is at least 2, 3, or 4. In the second case, 27 is 3 cube into 2 into n. 30 is 2 into 3 into 5. So 2 and 2 cancel, 3 squared, 5. So we get 9n by 5. Clearly, for this to be an integer, n has to have the power of 5 as 1. So this case also goes away. So when we are writing n, we have 3 possibilities for the power of 2, 1, 2, 3 possibilities for the power of 3, and 1 possibility for the power of 1. So the number of possible values for n is 9. Again, not a very difficult question. Basic concept of counting values is something that we should know. Moderate level, 2.5 minutes, good enough to answer the question. So if you look at the overall paper, as said initially, moderate sort of a paper, good attempt will definitely be six odd net correct answers. And the questions that I would attempt in this test, the 6 questions for me would be 1, 3, 5, 7, 9, and 10. Which are these questions? Definitely this one, because the basic application of LCM. Here, counting palindromes might be a problem, especially for 7, so might not attempt this. Certainly not in my top 6. Would attempt this every single time, just looking at factors of 2010. This could be a problem because the factor theorem or remainder theorem is something that we have to know to proceed. This is always something that should be done. Direct application of divisibility test. This 5, 6. Again, 3 raised to power 2018 minus 1. After that, it could be a problem. So not in my top 6. Would have done this because 28, 29, 30, we can see that they are divisible by 13 square. So my answer would have come from there, even if I'm not able to simplify the original expression. So would have attempted this. This I think was a good question, conceptual. Would have attempted this as well, counting numbers or multiples. And yes, would have attempted this as well. Numbers are easy in this question. And therefore 1, 3, 5, 7, 9, and 10 would be my attempt.